Hello everyone, my name is Samuel Okon. This is my presentation for the KaggleX Showcase Mentorship Program, which was on enhancing agriculture through computer vision-based plant disease detection. Allow me to introduce myself. I hold a BSc in Electrical and Electronic Engineering from Federal University of Technology, where I am an intermediate machine learning engineer with 2 years of domestic experience, and I'm passionate about continuous learning and staying up to date with latest trends. I'm also very enthusiastic about combining software engineering and machine learning, and I have a deep love for robotics. You can find me on my socials with those links. The goal of this project was to develop a computer vision based solution for plant disease detection for farmers, as it will empower farmers and provide timely and accurate plant disease identification, and also give an early intervention to reduce crop loss and improve agricultural productivity. This project is motivated by its potential to address critical challenges in agriculture. It can enhance food security, reduce economic losses, and promote sustainable farming practices, a few to mention. For this project, two datasets were used to improve the robustness, and both of these datasets were gotten from Kaggle. For this project, three methods were actually experimented with to see which is scalable and less stressful to set up. The first was transfer learning, which involved leveraging pre-trained state-of-the-art model and fine-tune on the dataset to perform plant disease detection. The second method involved using yellow beard to train an instance segmentation model to identify multiple plant detection in an image, and the last model involved using a multimodal model. Now, for the first method, this is the model architecture that was used to train the model. The input layer takes an image in the shape of 224 by 224 by 3, and it passes it through the mobile net feature extraction model. The output is sent to the global average pooling to reduce partial dimensions. A dropout layer was added to reduce overfitting, and finally, a classification layer was added with an activation function of softmax, which gave an output, a probabilistic output. So in the training phase, this involved fine-tuning the custom model with specified parameters like epochs, learning rate, and so on. And after training, an accuracy of 96% was achieved. And the graph on the left shows the training and evaluation results. Merging the second dataset with the main dataset revealed data imbalance across classes. The original dataset had varying image counts for each class, and adding the cassava dataset worsened the case. If a model was being trained with this dataset, it would lead to a biased model and poor performance. And so some steps were taken to address this data imbalance. So in order to address this imbalance, the steps involve data downsampling, in which I selected a consistent number of 1131 images from each class, fine-tuned the base model, and allowed training from the 100th layer onward, and data augmentation techniques like flipping, sharing, and brightness were incorporated. After implementing this adjustment and fine-tuning, the model's accuracy significantly improved, reaching an impressive accuracy of 96.78%, as shown on the table and on the graph. Method 1 is effective for image classification but has limitations in scenarios requiring new data distribution or multi-disease detection on single image. Method 2 overcomes this limitation by combining SAM for automatic data labeling and YOLO for accurate multi-disease leaf detection with very little training data. For method 2, the diagram below shows a high-level process that was involved. Firstly, images were being uploaded to RoboFlow, and then RoboFlow Smart Polygon feature uses SAM to automatically segment the images. And then these images were then resized, and some data augmentation techniques such as flipping, sharing, and brightness was incorporated. Then finally, the dataset was exported in a compatible format, and then a yellow V8 instant segmentation model was trained. And these are the results that were obtained after training the model. The metrics indicate high accuracy in object detection and segmentation. And method 3 was actually motivated by the fact that a farmer might not quickly be able to identify a plant disease and needs an expert. Lava eliminates this. As you can see in the attached screenshot, a picture of a diseased plant was uploaded, and Lava accurately diagnosed the ailment and suggested a remedy without specific training data. This advanced system shows great potential for agriculture, streamlining disease detection for farmers. And now I'll be demoing the project web app. It was designed using Streamlit. It was designed in such a way that a user could use a camera to take an image of a plant, and as you can see, it gives a prediction of the disease. And also, a user might be able to select images he or she has snapped, and then would get predictions for those images. Then, based on those detected diseases, I can actually go ahead and chat with the AI and ask how I can overcome this. And as you can see, the AI suggests some steps I can take to overcome or treat or prevent this disease. In conclusion, method 1 relies on pre-labeled datasets and requires substantial manual effort to achieve a high-performing classification model. The versatility of the Lava model makes it perfect fit for scenarios where farmers may struggle to identify specific diseases, and employing SAM and Yellow shines in situations with dynamic data, multi-disease classification, and minimal labeled data. And that brings me to the end of my presentation. And I want to say a very big thank you to KaggleX for this wonderful opportunity, as I've learned a lot from my mentor and other mentees. The links to the relevant project details can be accessed through the links provided below. Thank you.